Hey, College Algebra. What we're going to be doing is looking at section 2.7, graphing techniques. And this is actually a very big section, so this video might be a little long, so just bear with me, okay? What we're going to be looking at in this section is something called stretching and shrinking of graphs of our functions, and also something called reflecting. And something that goes along with reflecting, we might see something called symmetry. And then also something that goes along with symmetry are things called even and odd functions. So we'll be looking at determining how to tell whether a function is even or odd. And then finally, something called translations. Y'all might remember translations and reflections and stretches from my geometry class. Remember in geometry, shrinking and stretching was called dilations. And then reflecting, well, we just called those reflections. And then translations, remember those were when our images moved left or right or up or down or both. So that's what we're going to be doing with our 6 basic functions that we learned about in the last section. And we're going to be doing all sorts of things with those graphs that deal with the stretching and shrinking, reflecting, and translating. So first thing that we're going to look at is vertical stretching or shrinking of a graph. And this is how we determine if it is a vertical stretch or a shrink, algebraically here. So if we have a multiplier on our whole f of x function, like we have y equals f of x, and we have a value of a that's being multiplied to it. And this right here is going to tell us that we have a vertical stretch or shrink. And if our value of a is greater than 1, that tells us it's a vertical stretch. And if it is between 0 and 1, so like a small decimal, 0.1, or a fraction like a 1/2, 1/4, something like that, you have a vertical shrink. So let's take a look at an example. Oh, before we take a look at an example, let's look at what horizontal stretching or shrinking looks like. For horizontal stretching or shrinking, what you have is, again, you have a multiplier on some value of your function. This time, it's being multiplied to your value of x instead of your whole function. And whenever we multiply a value of a here in this case to our x before we square or take the square root of it, of one of our basic functions, this is what happens. We have something called a horizontal stretch or horizontal shrink. And it's kind of reverse. It is reverse of what a vertical stretch and shrink is. Whenever you have your value of a, your multiplier on x, is between 0 and 1, your graph of your function does something called a horizontal stretch. And whenever your value is greater than 1, then you have something called a horizontal shrink. So now, let's look at a couple of examples. All right, so in this example, like many of the examples you'll see in this video, we're going to be looking at the x squared function, our squaring function, as the previous section called it. Just note that we can stretch, shrink, reflect, and translate all those basic 6 functions that we looked at in the previous section. I'm just mainly going to be using the squaring function here as a good example for all the different types of things that we can have done to a graph of a function. Let's look at this one real quick though. We're asked to graph the function of g of x equals 2x squared. So like I said, it goes with the x squared function. So let's just find values of this f of x equals x squared with these 5 x values, and then look at the g of x function. I'm going to compare the two of them. So f of x equals x squared. If we plug in -2, we get 4. And then -1, we get 1. 0, 0, 1, 1, 2, we get 4. Now, for our g of x equals 2x squared, Notice the 2 is being multiplied to our x squared. So to get from here to here, we just need to multiply by 2 to get our value of g of x. So we're multiplying 2 to the entire function instead of multiplying 2 just to the x value, like in a horizontal shrink. So this right here is a vertical shrink or stretch. So let's see, multiply 2 to 1, we get 2. 2 to 0, we get 0. 2 and 8. All right, so now let's compare it. Now let's graph or plot some of our points here. We have 0, 0 still for our g of x. That's what we're graphing right now, is our g of x, because already graphed on our nice graph here is the f of x function. This is f of x. That's why I kept it in red. So let's graph another 2 points. So 1, or negative 1, becomes 2 up here. And so it does 2 over here, or the 1, 2. And then negative 2 and positive 2 go all the way up to 8. So now we can draw a nice smooth curve connecting all of these points. And notice that the graph of our g of x function compared to our f of x function, it looks different. What happened to all of our values from the original function, it got stretched upwards. It stretched vertically. So the point that was here went up to here. And the same thing, the point that was here at 2 went all the way up to this value up here. So that's why we call it a vertical stretch, is because all of our y values from our basic function got stretched upwards at our same x value. So at our, like I said, at our same x value of x equals 1, the basic function was at 1, but we multiplied it by 2 on the outside, and so it went up to 2. Here at 2, it did it again. What was here at x equals 2, which was 4, it got stretched upwards to 8. So that is why we call it a vertical stretch. Even though it kind of looks like the graph shrunk inwards, just think about it the other way. It got longer is what happened to this graph of the function compared to the basic function, f of x equals x squared. All right, so let's look at another one. Now we're going to graph the function h of x equals 1/2 x squared and compare it back to the basic function we know as x squared. Let's find some of the x squared y values and then the h of x function values. So here we're going to get, again, 4, 1, 0, 1, and 4. Now to go from here to this point here, notice we're, again, multiplying a value to our x squared function on the outside of the function, not to x first, but to the whole function. And this is what we're going to end up getting. So 1/2 times 4 gives us 2, times 1 is 1/2. 0 is still 0. 1/2 and 2. Now let's plot these points. 0 and 0, still there. 1 is at 1/2. So right there. Same goes for negative 1/2, or negative 1. It's at 1/2. And then negative 2 and 2 are at 2. 2, it's at 2. And that's at 2. All right. So this is kind of how our function of our h of x squaring function is going to look. Looks still like a parabola, like our x squared function. It's just been, this is called the vertical shrink. And the reason it's called a vertical shrink, like the vertical stretch, all of our y values from our original function here, all of our y values got smaller because it was multiplied by something between 0 and 1. So when our y values get smaller, well, that gives us a vertical shrink. In the next example, we're going to look at something called the horizontal shrink or stretch. And the reason that this is going to be a horizontal shrink or stretch is because our multiplier is going to be multiplied to our x and then it's squared, okay? So let's look and compare the x and y values by plotting a table here. So we have, again, our function x squared. Those values stay the same. And then, like I said, we're going to multiply it by 1/2, the x value by 1/2 first, and then square it. So these are the values we're going to get. So when we multiply 1/2 to -2, we get -1, and then we square it, we get 1. And then same goes for -1. Multiply it to 1/2, get -1/2, square it, we get 1/4. 0 stays 0. Then these values we already know. All right, so now let's take a look at this graph and plot the points for it. So we have the point 0, 0 still on this graph. Now we get to graph the point 1, 1/4, and also -1, 1/4. So it's about here on my graph, and here, and then plot the points -2, 1, and 2, 1. All right, so if you keep plotting points, you'll notice that your graph will look something like this. Okay, and this right here is called a horizontal stretch because our graph of our function just got wider. And I think the horizontal stretch and shrinks are actually easier to see versus the vertical horizontal stretch and shrink. I don't know, you may be a visual person, be able to see it just as well as one or the other. But on this, just note that if you have a value that you're multiplying to your x first before you square it or take the square root of it or whatever your basic function is, just remember, if it's between 0 and 1, it's going to be a stretch. If it's greater than 1, it's going to be a shrink. Now we're going to look at something called reflecting, and whenever we reflect a function across the x-axis or y-axis or the origin, we are flipping it. We're creating a mirror image of that function across a certain axis. And that is what we're going to look at mainly, is the x-axis, y-axis, and the origin as our reflection lines. Here is a function, our absolute value function. And let's compare the graphs of the basic function, the absolute value of x, to our g of x function, the negative absolute value of x. What we get for our points here, when we plug in -2, we get let's see, we get 2. Remember, absolute value of any number, any negative number, just becomes that number but the positive value of it. And the positive values stay the same. Now let's look at the g of x function so we can graph it. The negative absolute value of -2 is going to be -2. And then the negative absolute value of -1, -1. -0 is just 0. Then we're going to have -1 here and -2 again. Now let's plot these points. So we get -2, -2, -1, -1, 0. See what the graph of this function is going to actually look like? It's going to look the same as the red one, but it is being reflected across the x-axis. So here, what we see is whenever we have a negative value being multiplied to our entire basic function, we have a reflection across the x-axis. Okay? So again, we're going to have a reflection across the x-axis. Let's take a look at the basic function of our x squared function. So I'm comparing it to, not x squared, but our square root of x. Sorry for the confusion. And then our g of x function we're given to graph is the negative square root of x. Okay, so when we plug in these points, our x values 0, 1, 4, 9, 16, this is the graph that we're going to get for that, but let's get our function values. It's going to be 0, 1, 2, 3, and 4. And then the negative square root of x for those values are just going to be, they're all going to become negative because the negative is on the outside. Okay. I meant for all of those to be in blue, but let's pretend they are. Anyway, let's plot those points. So 0, 0, right here. 1, -1, right here. 4, -2, right here. That's all I can plot on this graph. We just need to connect these. And you see how it is that same basic function just flipped over the x-axis. And that is called a reflection across the x-axis. And remember, that's when we multiply our whole basic function by a negative value. Okay, what I'm going to do here is we're going to look at reflecting across the y-axis. And the reason this is a reflection across the y-axis is because we are multiplying the negative to just our x value, not to the outside of the function, but to the inside of the function. And the red graph that you see over here is still our function that f of x equals square root of x. And now we're going to look at graphing the square root of negative x. And the only way we can get the graph of the square root of negative x is if all of our x values are negative themselves. Because remember, if you have a negative inside a square root, you have an imaginary number. So let's look at this function here, which is the square root of negative x. We're going to get 0. Square root of negative 1 is 1. And that's going to be 2. And that's going to be 3 and then 4. So plotting those points, we have 0, 0. And then -1, 1. It's going to go here. -4, 2, -4, 2. Okay, and we keep on going with those x and y values. This is the function that we are going to be graphing. And notice it's the same basic function, just flipped across the y-axis. So this is a reflection across the y-axis. Here's what you're looking for when you're reflecting across an axis. So when you have a negative being applied to your basic function on the outside of the function, then it is reflecting across the x-axis. And then whenever you have a negative being applied to your x value before it's being squared or taking the square root of to whatever your basic function is, then it's the same as reflecting across the y-axis. To kind of go along with the reflecting across the x and y-axis, you have something called symmetry with respect to an axis, and you can have it again with respect to the y-axis or the x-axis. And algebraically, this is how you would work it out. If you have something that is symmetric with respect to the y-axis, this means you can replace your x with negative x, and your result is the equivalent equation to what you started with. And then the same thing goes with symmetry with respect to the x-axis. If you replace your y with a negative y, and result is the equivalent equation to what you began with, you got the symmetry with respect to x-axis. So here is testing for symmetry with respect to an axis. Now I'm just going to show you that the basic function absolute value of x is this right here, what I graphed, and the x values, or the f of x values, are going to be 2 if you plug in -2, 1, 0, 1, and 2. And then for the h of x, you're actually going to have the same results. Because remember, if you have a negative inside an absolute value, it's going to turn out positive anyway. So you have 2, 1, 0, 1, and 2. So if I were to graph my h of x, it's actually the same as my f of x. It's going to be the same graph. Okay? And so what we have here is symmetry with respect to the y-axis. Okay. Now, very similar, if we were to just plug in a negative y, let's do this algebraically. If we were to plug in x equals, plug in a negative y for our y, all negative values of y are going to end up turning positive. So the equation turns out to be the equivalent of this right here, the thing that we started with. So we're going to have something that looks like this graph that I already have on here. And you can see that our line of reflection right here, or our line of symmetry, is the x-axis. What you see up here is reflected down here. All right? So that's how you can look for, on your graphs, graphically, for symmetry, is if you have a line, a mirroring line at the x-axis or the y-axis. All right, so here is an equation of a circle, the x squared plus y squared equals 25, and that's already graphed for you here. And you can see that this thing is going to be symmetric with respect to the x-axis and the y-axis. Both of those are considered symmetry, lines of symmetry there. But algebraically, here's the way you're going to do this. Wherever you see your x value, what you're going to do is plug in negative x. And then we're going to test for symmetry for both axes by solving it algebraically. I'm just going to do it all in one fell swoop. I'm going to plug in negative x and for our x, and I'm going to plug in negative y for our y, since that's how you test for symmetry for x and y axis. And the results of this, whenever you square something negative, it turns out positive. Same goes for y. When you square something negative, it turns out to be positive. So what we have here is an equivalent equation to what we began with. And this means we have a symmetry with respect to both x and y axis. Okay, so something that is called symmetric with respect to the origin is when we replace our x with negative x and our y with negative y, kind of like I did with the previous example. And then those results of our equation turn out to be equivalent to the original equation. And that means we have a symmetry with respect to the origin. So let's take a look at this one. We're asked to figure out if this graph right here is symmetric with respect to the origin. And so we're going to do it just like it told us to do. We're going to replace our y with a negative y and our x with a negative x. And if our results turn out to be the same as y equals negative 2x cubed, then it's symmetric with respect to the origin. And then I'll show you graphically how it would look. Okay, so we have negative y, that doesn't change. And then we have negative 2, and then anything negative to the power of an odd number is going to turn out negative. So this is actually going to become positive x cubed. Now we have this negative over here still, so getting rid of it, multiply both sides by negative 1. We end up with negative 2x cubed, which is equivalent to our original equation. So that tells us this is symmetric with respect to the origin. And if we come over here to the graph that you see here, and let's look at it where we are reflecting this over the x-axis. So let's reflect it. If we reflect it, we're going to have a graph that looks something like this. Now reflect that line that you see in red across the y-axis, and then we're going to end up with a line that looks like this. The same original graph of our function. So that's how you can take a look at it if you want to graph your function and say, okay, if I flip this across the x-axis and then I flip it across the y-axis, will I end up with my original function, the original graph? And if that is true, then you have symmetry with respect to your origin. Now let's look at this function and see if it's symmetric with respect to the origin. I can tell you right now, it's not going to be. If we reflect this function right here, let's look at the graph of it first. If we reflect that across the x-axis, let's see. This right here, let me get my red out. This is what we're going to get. We're going to get a function that looks something like that. And then if we reflect that graph of that I just drew in red, if we reflect that across the y-axis, it's still going to look like this, what's in red. So that is not the same as our original graph that's in blue down here. It's not the same. So we're not, this graph of y equals negative 2x squared is not symmetric with respect to the origin. Let's solve that algebraically though, by plugging in negative y in for our y and negative x for our x value, and seeing if we come out with this, which I can tell you right now we're not, just by doing it graphically. So a negative value squared is going to become positive. And then if we multiply both sides by -1 to get y by itself, we're going to end up with a positive 2x squared, which is not equivalent to what we started out with. This right here is this. This right here is that. We do not have the same graph, so it is not symmetric with respect to the origin. Okay, you can pause the video right now and read these important concepts. They're also in your book, but I'm going to go to the next slide because it has a better visual of what this thing is actually explaining to you. Okay, symmetry with respect to x-axis. What you have to remember is the equation is unchanged if y is replaced with negative y. So for example, this function right here, it would be flipping across that x-axis right there, and the graph of that equation doesn't change whatsoever. And then the y-axis, if x is replaced with a negative x and it is unchanged, like for example this right here, if we were to flip that across the y-axis, we would have the same graph. And then symmetry with respect to the origin is replaced with x is replaced with negative x and y is replaced with negative y, and the equation is unchanged. So taking the graph of this function right here, if we flip it across the x-axis and y-axis, it becomes unchanged. Therefore, it's symmetric with respect to the origin. So remember these. You're not going to have any visual aids or anything to remember on your tests or quizzes, but you do have your graphing calculator, so use that to your best ability. All right. To go along with symmetry, we have something called even and odd functions. And an even function, its graph is symmetric with respect to the y-axis. And for odd functions, its graph is symmetric with respect to the origin. But I'm going to show you how to solve these even and odd functions to determine whether it's even or odd algebraically. And this is how we're going to do it, is by replacing our x value with negative x and seeing if our equation is equivalent to our original function, f of x. And then for odd functions, if we replace our x value with negative x and our equation is equivalent to the negative f of x, then it's an odd function. But we can have functions that are neither even or odd, and we'll discover that here in just a bit. So here we are asked to find whether our function is even, odd, or neither. And we're going to start out by replacing all of our x values with negative x. So replace even inside our g of x, replace our x with negative x. And then every other x in here, replace with negative x. Now, reduce this. So remember, anytime we are taking a negative value to an odd power, it's going to stay odd, or stay negative. So this is equivalent to negative x to the fifth, and this is equivalent to negative 2x to the third. And then negative 3 times a negative x, that's going to be positive 3x. Okay, so now what we're trying to do is see whether we have an even, odd, or neither. And how we're going to discover if it's even is if this right here, what we ended up with, is equivalent to our original function, which, no, it's not. We have negative x to the fifth minus 2x to the third plus 3x, not the same as this. So at this point, to see if it's odd, because we now know it's not even, take out a negative, factor out a negative, in other words. So I'm taking a negative out from our first term and from our second term and our third. And now this right here that's inside my parentheses is equivalent to this up here, is equivalent to our g of x. So what this is g of negative x is equal to the negative, see this negative right here, negative g of x. And if this statement is our result, what we have is an odd function. Okay? So that's how we determine if it's odd. Now let's look at a function that's going to become even or neither. For this example, we start out the same way as the previous one. We replace our x with negative x. So let's just start out doing that. And now we're going to see if our results are even, odd, or neither by determining if h of negative x is equal to negative h of x, or if our h of negative x is equal to our original function, h of x. Okay? So rewrite this. And now we have a negative value that's being squared. Anytime a negative value is being raised to an even power, that means it's going to become positive. So this is equivalent to 2x squared. And then minus 3 stays the same. So here we have the same as our original function we started out with. Therefore, our h of negative x is equivalent to h of x, which is by definition even. Okay, so there's an even function. Now let's look at this. I'm going to start out the same way as we did in the previous two. Replace the x value with negative x. And now what we're going to do is simplify it a bit. So negative x squared is equivalent to x squared. And then this right here is negative x, or 6x, plus 9. Well, it's not even because this does not equal that. Now let's see if we can take out a negative like we did in our first function, our odd function, to see if it's odd. So factor out a negative. What we end up with is negative x squared plus 6x minus 9. Well, the inside of this right here is not equal to that either. So what we have is a function that is neither. So if we can't show that it's even or odd, it's going to be the last thing. It's going to be neither of them. The last thing that we're going to be looking at are translations. We're going to be looking at vertical translations and horizontal translations. And here we have defined is a vertical translation. And what it is if we have a function, one of our basic functions that we are looking at in this section, and we add or subtract a value like this right here is doing. If we add or subtract a number to our function, then we have something called a vertical translation. It's going to move the graph up or down, depending on that value of c there. So it's similar to our vertical stretches or shrinks. We had a value that was being multiplied to one of our basic functions, to the outside of our basic function. The vertical translation is similar. Instead of being multiplied to our function, it's being added or subtracted to our function. So here's a vertical translation, a little pictorial representation of it. So you have an original graph that's down here. And if we add a value of 2 to that graph, what happens to it is it shifts upward. And if we subtract a value to it, like 3 here, it shifts down 3. Okay? So that's what a vertical translation does. So here is an example of a vertical translation. And we are moving our graph up 2 units, is what this is telling us right here. We're taking the x squared graph, our basic x squared function, and adding 2 to it. So it moves everything vertically up. So we're going to compare it a little bit to what that basic x squared graph looks like. And what it looks like, something like this. If you remember our basic function, x squared. And then the one that's being shifted up 2 units, the vertex would begin right here. And then the rest of our points would be graphed like that. Now, say instead we were actually subtracting 2. What happens to our original function, the x squared function, instead of moving up 2 units, it would move down 2 units. So it would move this vertex down along with every other point on the graph, and you would have a graph that looks like that there. Okay, so that's a vertical translation. Here is a definition of horizontal translation. What we have here is similar to our horizontal stretch or shrink. Comparing it to it, we had a multiplier on x that was just on our x value, not to the whole entire function. And what happened to it, it stretched it horizontally or shrunk it horizontally. And this right here, instead of the minus c or plus c being out here on our entire function, or being added or subtracted to our entire function, it's being added or subtracted just on the inside to our x value. Okay? And what this gives us is something called a horizontal translation. It shifts our graph left and right depending on whatever our value of c is. Okay? So let's look at an example. Well, here, before we move on to our example, is just a quick representation of what a horizontal translation will look like. We have the basic function here, our graph of our original function, and then if we add 2 to our x value, what happens to it is it shifts it over 2 to the left. You would think adding it would make it move positively, but in this case for horizontal, it does the opposite effect. So when you have a horizontal translation that goes to the right, like this one, it's being subtracted from x. Okay, so let's look at an example. Here we have, again, our basic function is x squared, but see how we are adding or subtracting before we're squaring it? That is going to result in a horizontal translation. Oops, don't want to draw in green. Let's see. Blah. There. So let's look at our basic function again. Here it is, x squared. And doesn't that look lovely? Yes. Anyway, what is going to happen to this graph right here is it's going to translate over to the left 4 units. So my vertex of my original function will move over 4, and so will every other point on this graph. It moves over 4 units. And the resulting graph looks like this. So it looks like our original function just moved over to the left 4 units. So now let's look at a combination of, I'm going to go in order here, of a reflection, because this is a negative value being multiplied to our function, and then this is a horizontal translation, and this is a vertical translation. Let's put all of those together on our graph. And this is how I'm going to tell you to sketch your graphs too. You're not necessarily looking for exact values, although I would like for you to get as close as possible many times. But what we're going to have here is our original graph. Let's compare it to our original graph, our x squared, because right here it's a squaring function. Okay, and it is being reflected across the x-axis. Remember, if we put a negative to the entire outer function, and that's what this is telling us, it's on the outside of our function x squared, it is going to flip across the x-axis. So I'm going to draw that in green here. So it flips. And then we're going to shift it over to the right 1 and then up 4. And that's what both of those are telling us. So I'm going to plot me a point on this graph. So 1, 2, 3, 4 up and over 1. So my vertex of my graph is going to be right here. And it's going to look something like that. Okay, so there is the graph of f of x in blue there, as best as I can sketch it out for you. And that's how you're going to graph your translations and reflections and all the other things that we have looked at. But one more thing before I let you go. This slide right here covers everything that we have just looked at in this section, and I'm going to compare it back to the squaring function that we've been actually looking at so much in this section, this lesson here. But if we go back and take a look at everything, all of our basic functions can be put into this form like I showed you on the previous section. If you wrote those down, great. If you didn't, go back and do that. But this is how it compares back. If we have a plus k, we have a translation up so many k units. If it's a minus k, then it goes down that many units. And then here, if we have a value being added or subtracted to x, then if it's plus h, then it goes to the left that many units. If it's minus h, like this right here, it goes to the right so many units. And then here it says if we have a multiplier of a right here that is going to be greater than 1, you have a vertical stretch. If it's between 0 and 1, you have a vertical shrink. Now here, if you have a multiplier on x that is between 0 and 1, then you have a horizontal stretch. And if it is greater than 1, you have a horizontal shrink. Now, if this value of a right here is negative, then it's this right here. It is a reflection across the x-axis. And if this value of b right here is negative, then you have this right here. It is a reflection across the y-axis. So there you go. That is the rundown, the summary of graphing techniques that you will just need to make a mental note of. Remember those as best as you can, and you will do well on this next section of homework and test that we will be having over this. But I am done for now, thank goodness, and I will see you in class.